Hey everybody, in this next video lesson, we're going to begin talking about the concept of equilibrium, or in other words, reactions that happen reversibly. We'll begin with reversible reactions. Some chemical reactions, when take the reactants and produce the product, what happens is as soon as that product gets formed, it actually begins to re-react and form the reactants. This is what is known as a reversible reaction, or a reaction that occurs simultaneously in both directions. So, at time zero, at the beginning, you just have reactants and no products, but as soon as the products begin to form, the products then become the reactants for the reverse reaction. So if you have all SO3, this reaction would happen from right to left. If you had all SO2 and O2, this reaction would happen to the right. But eventually, the reaction proceeds both directions and achieves a state of equilibrium where you have a little bit of both reactants and product in the beaker at the same time. Now, because these are reversible reactions, we don't just represent an arrow pointing in one direction, but we have a double-sided arrow representing reversibility. Now, this concept can be shown using a little bit of demonstration, and I'm going to ask Mr. Dirksen to chime in here using a demonstration with a little bit of green water. Check it out.
Okay, this little demonstration kind of helps us with the idea of equilibrium and reversible reactions. So what we see here, to start off, we have colored water, some green water here. That represents our reactant side of our process. And then, of course, we have our empty container over here that represents our product side of the process. So on any good reaction, when you start the process, everything's a reactant. So we all have all the water over here, and nothing is a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So on our very first scoop, if I'm using two identical beakers, if I go in here and scoop, on the very first scoop, all of it is going to be reactant turning into product and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now, if I continue to scoop like this and continue to do this, you'll notice how at first the reaction ran really fast. And at first, a lot of water was switching sides, going to the product side. But then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that I scoop going each direction will become the same. So if I look, I have 250 milliliters here, and I only have 200 on this one, so I'm not quite there yet. Okay. So now if I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, and again, this is not perfect measurements, but if we look at our volumes there, they're almost identical, which is showing that the amount that's crossing from here to here is equal to the amount going this way. Now, the amount in the beakers represents the rate. Okay, so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay? So the amount I take from here goes here, the amount I take from here goes here, and that process will never end. So this reaction now is basically over. It doesn't mean it doesn't keep reacting. It just means it's not going to change anymore. So we've reached equilibrium. So if we go back to the graph on our slide, we would see that this is the first one, or the top one, where the rate flatlines and becomes equal. Now, it doesn't mean that we have to have equal amounts. If we look at our tubs, because I was using the same size beaker, the volume level in the tubs are also very similar. So you'd almost get the indication that maybe the amount in each side has to be equal. So it has to be 50% this, 50% that. And that's not necessarily true. If we reset our setup here, and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product side. So in our very first scoop, again, it's all reactant, no product. Again, I start scooping and I get some product back to reactant. Okay. Now you might think there's no way you can get equilibrium here because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volume, which means if I pour 140 into here, and I pour 140 into here, there's no difference, okay? So I am now at equilibrium, okay? So switching again, I can do this all day long, and from this point on, there will be no change in the volume in either tub, which means this reaction from reactant side to product side is at equilibrium. Now in this case, if we look, we had equilibrium, but if we look on the product side, we have much more water than we do on the reactant side. So in this case, because we end up with more product, we would call this a product favored equilibrium. We have less reactant, so it is not reactant favored. If you flipped it, and if you had a scenario where at the end you had something like this, this could be an equilibrium. It might mean you're using the big beaker for the product side and this little guy for the reactant side. If that was the case, if you have very little product and a lot of reactant left over, this is a reactant favored equilibrium. So if we go back to the idea of the graph in our notes again, we see the bottom graph shows the amount, and in that graph reactants were in red and products were in blue, I believe. So that was a product favored. So let's reset that to look like product favored, where once you've reached equilibrium, the rate of transfer, or how much gets transferred across, again, our rate of transfer would be equal. So that would come together on the graph, but yet the amount of product would be more than the amount of reactant. At equilibrium, this would be product favored, which represents the second graph.
Thanks, Mr. Dirksen, for that excellent demonstration. Take a look at this picture. It's the same old potential energy profile which we've seen before, which shows us the activation energy of a reaction in the forward direction. We take glucose and oxygen, there's a little bit of activation energy. In fact, all reactions require activation energy in order to perform. And in this case, the activation energy is represented by this purple, pink, magenta arrow. The activation energy achieves a maximum, and then the reaction can proceed to products. But in a reversible reaction, we also have an activation energy. And the activation energy would basically be the amount of energy to overcome the energy lost in this exothermic process, plus the original activation energy. So the activation energy in blue for the reverse reaction is larger than the activation energy for the forward reaction. But the point is that no matter if you're going forward or reverse, in each case, activation energy must be achieved, which is why this reaction, taking carbon dioxide and water, probably is a much slower and more difficult reaction because the activation energy for the reverse reaction is considerably higher than the activation for the forward. But this is what's happening in photosynthesis. Plants take carbon dioxide and water and turn it into food and oxygen. Fortunately for us, as we talked about, otherwise things that breathe oxygen would not be around. So plants can overcome this activation energy in order to reform the reactants in this reaction. The forward path, which is the oxidation of glucose, and the reverse path, which is photosynthesis. Now you've seen this graphic in the demonstration that Mr. Dirksen just ran us through, but we're going to talk about it again. He mentioned a little bit of the details, but I'm going to really hammer it home at this point. Chemical equilibrium is most often misconceived as having equal amounts of reactant and product at equilibrium, but that is in fact not the case. Chemical equilibrium is defined when the forward and the reverse reaction are happening at the same rate or the same speed. Take a look once again at this top graph, where rate is the vertical and time is increasing along the horizontal. At the beginning of the reaction at time 0, right here, the forward reaction is fast, and it slows down over time because the reactants get used up, and as concentration goes down, the speed of the reaction decreases, or the rate of the reaction decreases, as we mentioned in our last module. The reverse reaction begins nearly at 0, and instantly the reaction begins to speed up because as the forward reaction creates products, the reverse reaction can then speed up because the concentration is increasing of the products, and the reverse reaction rate can increase. But eventually, both of these lines come together, and once it turns from red and blue to purple, they now are at an equal rate and establishes equilibrium at this point right here, which I highlighted on the graph. Up until that point, they are not at equilibrium. But if you take a look at the same time period and compare the amounts, you'll see that the reactants begin very high in concentration and the products very low. Reactants decrease as time progresses, as you'd expect, because the reaction progresses in the forward. And then the products begin at 0 concentration, and they grow as the reaction progresses over time because the products get produced from those reactants. So reactants go down, products go up. At one point, they cross over each other, but that's not really all that important. The point is that they eventually stop increasing or stop decreasing. At that time, which I can draw a line on the graph, which represents the time at which the concentration of the product stops increasing and the concentration of the reactants stops decreasing. And that is defined as the time at which equilibrium has been established. So if you're taking a look at the rate, it's where the two rates come together. And if you're looking at the amount, it's not the amount when they equal each other, it's the amount at which they no longer stop changing. And one final observation about this picture down here is that because the products end at a higher concentration than the reactants at equilibrium, we consider this situation a products favored equilibrium because the concentration of the products is higher than the concentration of the reactants once the reaction reaches equilibrium. But let's say, for example, we have something very similar to the one up above, but instead the reactants come down and then the products grow. But in this case, the reactants end or establish equilibrium. I will put in a point. I know this is a poorly drawn graph, but I'm doing it quickly. But let's say establishes equilibrium at this black line where they no longer increase or decrease. I know, terrible drawing, but just for the sake of conversation, let's go with it. At this point, because the reactants, the red, is higher in concentration than the products, then this is considered a reactants-favored equilibrium. And as a result, we have more reactants at equilibrium in the solution than products. Very rarely will you ever have reactants and products coming together and meeting at equal concentrations. In fact, I've been teaching chemistry for over 15 years, and I haven't come up with an example of any chemical reaction that will actually do this. So, in summary, if your products are higher in concentration than your reactants at equilibrium, it's products favored. And if your reactants are higher in concentration than your products at equilibrium, then it's reactants favored. Going along with the information from that last slide, the position of the equilibrium is dependent on which is larger in concentration at equilibrium. And so if you have a reactant A making product B, and product B is higher in concentration than reactant A at equilibrium, then we would consider this to be a products favored situation. Whereas if A is larger in concentration than B once equilibrium has been established, then we call that a reactants favored equilibrium. And then sometimes we show the length of the arrow to represent the side of the reaction that's favored. So a products favored reaction would have a longer arrow towards the products and a shorter arrow back toward the reactants, basically meaning that this reaction doesn't produce as much reactants in the reverse as it does products in the forward. Whereas in this second example, we have more reactants created in the reverse than we do in products created in the forward. And so this slide is just here to show you what it means, or to establish what it means to be products favored or reactants favored. And a quick note, catalysts, which make reactions happen faster by providing an alternative pathway for the reaction to occur, do not affect the position of equilibrium. It only decreases the time needed to establish equilibrium. And so catalysts don't make it any more product favored or any more reactant favored. It just simply establishes equilibrium at a quicker speed. So we're going to finish with this slide, and I'm going to introduce to you something called K, or also known as the equilibrium constant. K is basically a number that is determined by taking the concentration of the products and dividing by the concentration of the reactants at equilibrium. Another thing about K is that it is a unitless value. It has no labels. Now the little brackets around products and reactants represent molarity of or concentration of. So whenever you see these brackets, it means concentration. So if your concentration of products divided by your concentration of reactants establishes a number that is larger than 1, then you have a products favored reaction. As you can see down here in this picture, we have red spheres making green spheres, and in this reaction at equilibrium you have way more green spheres than red spheres, and so you would have a K value that is much, much larger than 1, and this is a visual representation of a large K or a products favored reaction. Those mean the same thing. Products favored means large K value. Now if you have something that has more reactants than products, then the ratio of products over the reactants is going to be small, right? Because as the number on the bottom of a fraction grows, the actual value of the number gets smaller. And so we have a fraction or something that's much, much smaller than 1. Look at this example that says small k. We've got blue spheres creating red spheres, and it establishes equilibrium, and you've got a lot of blue spheres and very few red spheres. And that means that the number on the bottom is really big and the number on top is fairly small. And so this ratio is going to represent a fraction or a number much, much smaller than 1. And reactants favored equilibrium is another way of saying it has a small k value. Now, moving forward, we're going to actually put values or numbers to these k values. But for now, we're just trying to establish what it means to have a large k value or a small k value and show you some visuals. Now, this example is an intermediate situation where you have roughly the same amount of reactants and products. We have black reactants and green products, and we can count the number of products and reactants, and this is kind of an intermediate situation. This has similar amounts, and so your number hovers around 1 or about 1 because your products and reactants are about the same value. If you take the products divided by reactants, you get a number that's about 1. Now, in truth, I don't know many examples of reactions that are about 1. Usually they're 10 times greater than 1, so you got a large K value, or 10 times or less smaller than 1, and so you have a super small K value. But this is a possibility. I'm sure there's a reaction out there, and some nerd will tell me all about it after you watch this video. But just so you know, we've got small K values when reactants are high and products are low, large K values when products are high and reactants are low, and intermediate K values when they're about the same. This is a really important formula, products over reactants equals K, and we're going to work a lot with that moving forward. Well, that takes care of this video lesson. Thanks for watching.